So for our next speaker, we have Taiga Hiroka, who is going to talk about robust combiners and universal constructions for quantum cryptography. Please take it away.
Thank you for introduction. I am Taiga Hiroka. In this talk, I talk about robust combiners and universal constructions for quantum cryptography. This work is joint work with Fuyuki Kitagawa, Ryo Nishimaki, and Takashi Yamakawa. This is the outline of my talk. First, I will explain motivation, and then I will explain result about robust combiners and universal construction. Then I will explain result about plain text expansion of unclonable encryption. Now I will explain motivation. So far, it is known that there are several quantum advantages in cryptography. The first kind of quantum advantage is that we can construct useful cryptographic primitives from weak assumption. In classical cryptography, one-way function is essential for the existence of classical cryptographic primitives. This means that, for example, we can construct secret key encryption or digital signature or something like that from one-way function. On the other hand, although we do not know how to construct PKE, OT, or MPC from one-way function, still the existence of one-way function is necessary for the constructing of these primitives. So in this sense, one-way function is the minimum assumption for constructing a classical cryptographic primitive. If we consider quantum case, the situation is different. As explained in the previous works, we can construct pseudo-random state generators from the existence of one-way function. Furthermore, from pseudo-random state generator, we can construct several useful quantum cryptographic primitives such as quantum commitments or one-way state generator, which can be seen one of quantum generalization of one-way function. And as Krejcima pointed out, pseudo-random state generator exists even if BQP is equal to QMA. So in this sense, the existence of pseudo-random state generator is possibly weaker than the existence of one-way function. Okay? So this is the first kind of quantum advantage. And the second kind of quantum advantage is that we have several cryptographic applications impossible with classical cryptography. One example is public key quantum money. In public key quantum money, receiver receives money state, and roughly speaking, the correctness guarantees that everyone can verify its validity of the money state. On the other hand, security, roughly speaking, guarantees that no one can clone the money state. And another example is unclonable encryption. In unclonable encryption, the receiver receives a quantum cipher text of the message M. And roughly speaking, the security guarantees that no one can clone the cipher text. Okay? So obviously, these kind of cryptographic primitives are impossible to achieve with classical cryptography because in classical cryptography, we can trivially clone the classical data. So we cannot achieve these kind of cryptographic primitives in the classical world. So this is the background, and I will explain our motivation of our work. Although there is a possibility that these quantum cryptographic primitives are weaker than one-way function. However, all previous concrete instantiation relies on some assumptions such as LWE or LPN or something like that, which implies the existence of one-way function. But one of the original motivations of quantum cryptography is cryptography without one-way function, so it is natural to desire to have concrete instantiations of quantum cryptographic primitives whose security is more reliable. And another motivation is that although we can achieve these cryptographic primitives, such as public key quantum money or unclonable encryption, but the previous concrete instantiation relies on some computation assumption. So if the underlying assumptions are broken, in that case, these concrete instantiations are no longer secure. So ideally, we should give concrete instantiation of quantum cryptographic primitives whose security is more reliable. So for this background, our main question is that can we give concrete instantiations of these quantum cryptographic primitives whose security is more reliable? This is our main question. And our result is about robust combiner and universal construction. Okay. So again, our main question is can we give concrete instantiations of quantum cryptographic primitives whose security rely on more reliable assumption? And our result is to give robust combiners and universal construction for several quantum cryptographic primitives, such as quantum commitments, or one-way state generators, public key quantum money, and unclonable encryption. This is our main result. Now I will explain our result in more detail. So first, I will explain the definition of robust combiner. The robust combiner is defined for each cryptographic primitive. Robust combiner for some primitive P is a Turing machine that takes as an input a candidate of the primitive as an input and outputs a new candidate of the same primitive. And robust combiner requires that this new candidate must satisfy both correctness and security, as long as at least one of the original candidates satisfies correctness and security. This is a definition of robust combiners. And I will explain it in more detail by using the description below. Suppose that we have 4 candidates of quantum commitment, and by using robust combiner, we can obtain a new candidate of quantum commitment. And robust combiner roughly requires that this new candidate must satisfy both correctness and security, as long as at least one of the original candidates satisfies correctness and security of the quantum commitment scheme. So this property is obviously useful in a realistic scenario because, for example, some adversary might find attacks for candidate B, candidate C, and candidate D. Even in that case, as long as the candidate A is secure, our new candidate is also satisfies security and correctness property of quantum commitments. So it is natural to desire to have robust combiner for several quantum cryptographic primitives. And we give robust combiners for quantum commitments, one-way state generators, public key quantum money, and unclonable encryption. This is our one main result. And theoretically speaking, robust combiner is useful for constructing universal construction, which is theoretically important. The universal construction was originally introduced by Levin, and the universal construction is also defined for each cryptographic primitive. Universal construction of some primitive P is a concrete construction of the primitive, whose security relies on the existence of the primitive. This is the definition of universal construction. I will explain it in more detail by using the description below. Usually in cryptography, if we want to give concrete instantiation of quantum commitment, we give concrete instantiation by assuming the concrete assumptions such as hardness of LWE or hardness LPN. But one problem is that if we find some new algorithm that solve, for example, LPN, in that case, this concrete instantiation is no longer secure. So ideally, in cryptography, we should give concrete instantiations of cryptographic primitives whose security is more reliable. And universal construction is one of the most secure construction among all candidates of quantum commitment, because we can prove its security assuming the existence of quantum commitments in this world. So to break security of universal construction of quantum commitment, we need to find attacks for all other candidates of quantum commitment. So in this sense, universal construction is the most secure construction for quantum commitment. And in particular, in quantum case, one of the original motivation of quantum cryptography is cryptography without one-way function. However, all previous concrete instantiations rely on assumptions such as LWE or LPN, which imply one-way function. And we give universal construction for quantum commitments, one-way state generator, public key quantum money, and unclonable encryption. This is our result. Okay. But for time limitation, I cannot explain the technical details of it. So if you are interested in it, please ask me after this talk. Okay, this is the first result. And our second result is about plaintext expansion of unclonable encryption. Okay. In one of universal construction for unclonable encryption, as a corollary, we obtain the following result. We show how to expand plaintext space of unclonable encryption by using decomposable quantum randomized encoding. To explain it, I will explain the definition of unclonable encryption in more detail. So unclonable encryption was originally introduced by Broadbent and Rode in TCC 20. And the unclonable encryption is the same as standard secret key encryption, except that it requires new security explained as follows. In unclonable encryption, first, the adversary sends a pair of plain text, and then challenger randomly samples bit value B and the secret key, and generates quantum ciphertext of the message B, and sends back to the adversary A. After that, the adversary generates two quantum states, row B and row C, and sends them to the party B and party C respectively. After that, these parties receive the secret key of the quantum ciphertext. Then they guess the bit value of B by using these information respectively. Okay, here the point is that they cannot communicate each other after receiving the quantum state. And the unclonable security guarantees that in this procedure, this inequality holds. And obviously, we cannot achieve this security if the ciphertext is classical bit string. If the ciphertext is classical bit string, we can clone the ciphertext and pass the first ciphertext to the party B and the second ciphertext party C, and we can trivially break the inequality. So we need some quantumness to achieve this notion. And in previous work, it was an open problem how to expand plain text space of unclonable encryption. So we do not know how to construct unclonable encryption for multi-bit message from unclonable encryption for single-bit message. This is because in the cryptography, the standard technique for expanding plain text space is bitwise encryption. But bitwise encryption does not work in the unclonable encryption setting because of this security of notion. If we encrypt two messages by using a single bit message, in that case, the adversary can pass the first ciphertext to the party B and second ciphertext to the party C, then we can break the security. So bitwise encryption does not work in the unclonable encryption, but we resolve the problem by using decomposable quantum randomized encoding. Okay, this is the second result. Okay. Now I finally explain the future direction. One future direction is, in the classical case, we have concrete instantiations of one-way function. For example, we can construct from LWE or discrete log or RSA or something like that. But one possibly interesting direction is to find more inherently quantum assumption, which is plausibly weaker than one-way function, but still useful for constructing quantum cryptographic primitives. And second direction is to give universal construction for other quantum cryptographic primitives, such as pseudo-random state generators or pseudo-random unitary. And the third direction is to give universal construction by using meta complexity. In classical cryptography, we have universal construction of one-way function by using meta complexity, but we do not know how to do in the quantum case, so it might be interesting direction. So that's it. Thank you for listening.
Thank you for the talk. We have 2 minutes for questions.
So for the unclonable encryption, do you assume that the adversaries have some shared entanglement between them?
I guess so. Actually, I forgot, but I guess so.
Okay, thanks.
Actually, I have one. For your plain text expansion theorem, what kind of security definition do you assume for unclonable encryption?
So what do you mean?
What's the security definition that you assume that unclonable encryption
Underlying
satisfies?
unclonable encryption? So we assume the existence of unclonable encryption for single-bit message, and the definition is standard unclonable indistinguishability definition. And by using it, we can construct unclonable encryption for multi-bit message, which satisfies standard unclonable Indo security.
If there are no more questions, let's thank the speaker again.